Okay, good morning, everyone. My name is Anton Sokolov. I'm from DAISY Theory Group, being a PhD student there. And today I would like to tell you about my recent paper in collaboration with Andreas Ringwald, which is called Photophilic hadronic axion from heavy magnetic monopoles. So this model is quite basic, and in fact, I call it on the first slide as missed axion model because it could have been proposed, I think, 40 years ago, and it is not less simple, not less simple than the KSVZ model, for example. It is also very nice because it has the advantage of explaining many hints. In fact, it explains beyond, except the strong CP problem, it also explains the astrophysical hints such as the energy loss of the horizontal branch stars in globular clusters, and also the anomalous TeV-transparency of the universe. And it also can explain the cold dark matter abundance we observed today. So let me continue. The motivation of this work was just the observation that the electric and magnetic fields are introduced symmetrically in the Axion photon Lagrangian. So in fact, the vacuum Maxwell equations are known to be symmetric under the electric magnetic fields interchange, and they remain symmetric after introducing the Axion field. And then the question is, if in the KSVZ-like models, we introduce electrically charged heavy quark, and then we arrive at this electric magnetic symmetric structure, why not introducing a super heavy magnetic particle instead? And then probably we can arrive at the same effective Axion Lagrangian, but probably with another couplings. So let us try to introduce, instead of the electric U1 group, the magnetic U1 group, so to say, which means we consider magnetic monopoles. Let me review briefly the physics of magnetic monopoles, because not everyone is familiar with it. So actually, it all started back in 19th century with Pierre Curie proposing that there is actually no theoretical obstruction in introducing the magnetic monopoles to the Maxwell equations. In fact, you see that there will be some magnetic charge density and the current. And then in 1931, Dirac reviewed magnetic monopole in the quantum theory, and actually he found that that magnetic charges arise naturally in the quantum theory, just continuing the considerations which lead to the gauge principle. And however, the quantization condition is to be imposed. So the product of electric and magnetic charge should be equal to some integer times 2 pi. Since then, there were many attempts of building the quantum field theory of magnetic charges. And in fact, many scientists worked on that, including Schwinger, Fierz, and Dirac himself. And in the end, what we have now is Zwanziger's theory, where he succeeded to obtain a local Lagrangian for the electromagnetic dynamics, but he had to introduce two vector potentials, which are actually both describe one particle, the photon. So in fact, they are not independent variables, so to say. So this is not like the case of mixing when we have photon and hidden photon. But each of these potentials has only 1 degree of freedom. So in fact, the Lagrangian also looks not like in normal QED because we have a quite different kinetic term, which is quite cumbersome, so I don't give it here. But the important part is that it depends on some fixed 4-vector n. And then, as you can see, the theory is not manifestly Lorentz invariant. However, already Zwanziger provided some evidence that it can be Lorentz invariant, and indeed, in 1977, Zwanziger, Brandt, and Neri showed in the path integral formulation of this theory that the dependence of the theory on this fixed vector n disappears after performing the path integral. And the whole theory is Lorentz invariant. You just have to resum all orders, and you cannot work actually in perturbation theory here. So now let me talk about the model with the Abelian monopole. So let us introduce a magnetically charged quark. So and at high energies. So the high energy Lagrangian will look like this. And you see that here we have a part which comes from the Zwanziger theory. So this is interaction of the magnetic current with this vector potential B mu, which is introduced in the Zwanziger theory. And the coefficient is the magnetic charge. So due to the direct quantization condition, the minimal value of this G should be 6 pi over E. Yes, because we have the quarks which have the electric charge E over 3. So actually, let us now take this Lagrangian with phi being the Peccei-Quinn field, just like in the KSVZ model. So everything else is just like in the KSVZ model. And okay, we performed a linear decomposition of the Peccei-Quinn field, introducing the Axion field as the Goldstone boson after the spontaneous symmetry breaking of the Peccei-Quinn symmetry. And we obtain this kind of Lagrangian, where we actually can integrate out heavy monopoles by using the Schwinger proper time method. Now it is possible because of the separation of scales between the high energy physics, where which is given by the Peccei-Quinn scale, and VA. Yes, and the low energy physics, where we can perform experiments. So the effective Lagrangian is given by this expression, and you can see that as one could expect, we get the enhancement of order G squared, so magnetic charge squared, instead of the electric charge squared in the KSVZ model. And in fact, this is a huge enhancement of the photon coupling, which behaves as 1 over the fine structure constant squared. So let me review the phenomenology of this model. Here you can see the plot of the Axion photon coupling from the Axion mass, and the blue line here is prediction of the Abelian model. So the model with the Abelian monopole, which we discussed. So you can see that it lies in a region which will be probed by many future experiments, and it is already probed by the EDMX-SLIC experiment, but it also can explain the energy loss argument from the horizontal branch stars. So here it's light blue region here, and this region is accessible by future experiments such as IPS2 and baby Ajaxo, and it's quite interesting. Also, if we increase the value of the magnetic charge, which is not forbidden, then we can also get the model which explains the anomalous TeV-transparency of the universe. So it's region here, yes, which is denoted by arrows. So now let us go further and discuss even more symmetric settings. So we had a magnetically charged quark, but why not having the magnetically charged magnetic quark? So actually, it is known that not only abelian groups can have can be magnetic, but also non-abelian groups. So in fact, we can preserve the minimal direct magnetic charge. So here in the standard model, if we assume that the monopoles carry also the color magnetic charge. So what does it mean, the color magnetic charge? So it was the conjecture was put forward that actually the magnetic non-abelian magnetic charge is transformed under the representation of the GNO dual group, which is denoted by V here. It's also known as Langland's dual group in mathematics, and with the coupling constant, which is 2 pi over the coupling constant of the non-abelian theory. So here it's strong theory, and then for U1, this group, the magnetic group is the same, and for the SU3, it's the same with modulo some discrete group factors. So now we introduce the magnetic monopole, which is abelian and non-abelian, and so it transforms under the SU3 magnetic group. So then the Lagrangian takes this form, so everything is the same as in the abelian case, but we now have this connection not over the U1 group, but over the GNO group, so which has abelian part as well as non-abelian part. And in fact, we can now wonder if this model still solves the Stronsky problem. So in the abelian case, it solved the Stronsky problem automatically because we just had magnetically charged quarks. So in the strong sector, the model was just the same as a KSVZ model. So then in the abelian case, model with the abelian monopole, it was clear that it solves the Stronsky problem. But here we have a different group. Yes, we have SU3 magnetic, so it's color magnetically charged quarks, quark at high energies. So how to show that it solves the Stronsky problem? So actually what we do in the paper, we we just fix the gauge in such a way that we are left only with the abelian factors of the group. So these gauges are known as toothed abelian gauges and used in confinement physics quite frequently. And then one can show that under such such gauge fixing, the off-diagonal gluons obtain finite mass around 1.2 GeV, and actually then they do not contribute to the physics at the infinity, so which gives us the theta term of QCD. So then so it's just a simple intuitive understanding why only abelian field strengths tensors remain here in the theta term of QCD. And also we can do the same with the anomaly interaction of Axion with gluons, which arises from the chiral rotation in this Lagrangian, and modulo some derivative couplings of derivatives of Axion times something, it will be given by this expression. So in the end, you see that we have again that the Axion field just absorbs the theta parameter. And it happens because we are able to, under this integral, we are able to leave only abelian monopoles. Only abelian part of the gluon fields. So then the Vafa-Witten theorem ensures that this model also solves the Stronsky problem. Now coming to the low energy physics, it can be also shown that the Schwinger proper time method, which we used in the abelian case, can be easily generalized to the non-abelian case. And in fact, we get also the conventional FF dual term and GG dual term is the effective Lagrangian, but not only, because actually when we integrate out, we get the dual field. So here we would get some G dual, G tilde dual, and then when we want to come to the non-dual gluons, we are left with some additional contribution to the Lagrangian, which involves, however, only interactions of Axion with off-diagonal gluons. And these off-diagonal gluons are interactions are expected to be suppressed in the infrared because of the Abelian dominance in QCD, which is well known and shown both on the lattice and theoretically. So in fact, the Axion photon coupling is again has again very large enhancement, but also now it depends on the strong coupling of QCD, which is very unusual for Axion models. Also, one has to mention that because of this term in the Lagrangian, the off-diagonal gluon term, we do not have a universal coupling of Axion with gluons. So in fact, this model can be distinguished from, for example, clockwork Axion photophilic models because of this term. If one can measure this deviation from the universal coupling. So, okay, now let me discuss in the end the phenomenology of this model. So in fact, we get the similar plot to what we had for the Abelian model. So, but now it's we have a band instead of a line. So there is here I still show the line for the Abelian model, and for the non-Abelian model we have a band because actually the strong coupling in the infrared, which determines the Axion photon coupling as well here, it is not known exactly in QCD. So there are different determinations, and but the most used option is the value close to pi, to what QCD people converge, I think. And this value is also obtained from the ADS QCD considerations. So, and here it's shown as a dash dotted line. And in fact, one can see that for the minimal assignments of the magnetic charges for this high energy fermion, this line nicely passes through the TeV-transparency hint, anomalous TeV-transparency hint here, as well as the horizontal branch stars hint. Yeah, so this would be quite interesting because in future this region also can be probed by ABS2 in several years. Yeah, so thank you for your attention. If you have any questions, please proceed.